today, which is Riley Hales from Brigham Young University. And that will be talking about the GEOGloWS using the global forecast to enable local decision makers. I think, it will give us a little bit of insight of, how you can make, those type of models usable. So, Riley, if you're ready, please, take control of the screen and start your presentation.
All right, thank you. Great. All right, well, hello, everyone. I'm Riley Hales. I'm a PhD student at Brigham Young University, and I'm speaking about some work I've done over the past few years, supported by a partnership between ECMWF and GEOGloWS. That's a GEO project on global water sustainability. And the premise for my research is rooted in the worldwide need for data. And Leonardo and Walter have already spoken about this at length, so I will defer to their explanations. But suffice it to say, worldwide, everyone faces water scarcity, water quality issues, flooding risk. These problems come for us all in rich countries and poorer countries, developed, least developed parts of the world. And traditionally, the way that we've tried to address these problems, philanthropies, international organizations of many types, they try to address this need for data by helping these at-risk countries, those places most in need, to get funds to collect data, build water monitoring infrastructure, collect data sets, and build models, which they then take to the decision makers, train personnel, build the institutional capacity to use them. But like Leonardo mentioned in his anticipatory action slides, a lot of this happens after the fact. It doesn't always lead to lasting changes. There could be more benefits if it was a more continuous operation. So we've been, and this is, sorry, I got ahead of myself. This is what I've diagrammed on the top of the slide. And so we've been investigating ways that we could make this more sustainable by building global models. And so this is what I've shown on the bottom of the slide. What if rather than build models everywhere, trying to do this all after the fact, we could build a global model with a centralized repository of data, human expertise, funding, computer power, all the things that it takes to build a good model, and then provide access to the model with web services. And if we could make that work, we think this would be a much more cost-effective, long-term sustainable approach to get the data into the hands of those that need it most to solve these real issues that we all face. And so I'm going to zoom in on my slide on that bottom row. Really, I'd say there are two broad challenges to making this approach work, which I'd like to explain how we addressed in this presentation. First would be, can you actually build the global model that's sufficiently useful, sufficiently accurate? And two, can you make it usable? Just throwing my slide, my three arrows that say global services is a great idea, but there's a lot of work that goes into making that actually useful to the local decision makers. To be a little more specific, I'd say that these two challenges are going to be addressed in 5 ways, which I'll explain in this presentation. First, the two on the left, global data and modeling methods and having an operational computer environment to run the model. I'd call that part of challenge 1. And the global services that make the model accessible, I propose there are really 3 primary services that you can develop to make these models useful to decision makers. First would be a data service. That'd be providing access to the numerical results of the model, bulk downloads of data sets, and ways to query just subsets of the model results. The second would be a visualization and mapping service. As this global model would produce a lot of data, we need good ways to view it and inspect the results of the model without needing to download all of it and process it in our own unique ways. And last would be a series of web apps or other kinds of web interfaces to the model, which houses access to the data and mapping service, contains metadata and other information, a sort of homepage on the web for these models. So I'll start explaining the first two components, how we address challenge one, building a good model. We started building with results from the ECMWF Tesla land surface model, specifically the runoff data set. And I'll depict that as this colored square since it's a raster gridded data set. And we're taking their results because they're globally available and made possible through our partnership with them. And they're among some of the best data sets you could possibly use at the global scale. And next we used a delineated stream network, which I'll depict as this watershed outline. This is a GIS or vector data sets, which we specifically derived for this purpose. The stream network has about 1 million segments in it, and our model will produce results on each of those segments. Each of those river segments represents a drainage area of about 150 square kilometers, so that varies a little bit around the globe. Then we combined our GIS data set, the watersheds, with the runoff data set, which allows us to do a bunch of math. We know which cells intersect which watersheds. We know the size, the area of those cells, and we know the forecasted runoff depth in each of them. So we can figure out, just multiply those together, we'll get a runoff volume in each of those stream segments, the subbasins. And if we repeat this for each of the time steps and each of the watershed subsegments, then we can route across time over the period of the forecast through each of the subbasements and give us results over the period of the forecast. And we do that with Muskingum routing. And this produces two principal data products. We provide a hindcast or historical simulation based on the ERA5 reanalysis data set. That data set goes from 1979 to almost the present. And we update our model results monthly. So there's between 2 or 3 months of lag, depending on exactly when you go to get the historical data set. The second thing we produced is a forecast. This one's probabilistic. It's based on the same data sets as GEOGloWS. So it's ensemble forecast with 52 total members. And like GEOGloWS, we produce new results every day at midnight. So now I'd like to transition to how do we make these global data sets available to those that most need them. The first one I'll talk about is the visualization or map service. We developed this in collaboration with our partners at Esri. This is a view of the global map. And if you notice, there's some variation in the size of the river segments and colors as you go across the globe. So I'll zoom in. On the left, here's a zoomed in view of the river network. And on the top right, there's the legend for the mapping service. This is on the left side of the legend, there's a color scale that indicates whether or not we forecast that river segment is going to exceed a return period, which we compute from the historical simulation data. And on the right, the different thicknesses of the lines that represent the rivers corresponds to how much we predict or how much flow we predict will be in that river segment. And this map service, along with the base maps shown on the bottom right, are available on the Esri Living Atlas, so they can be consumed by any web app, GIS software, anything that accepts web map services. But because this covers a forecast, this changes throughout time. So I've got a demonstration video that illustrates how this goes with time. On the bottom center of the screen, you'll see a slider that shows the time, and then the map shows the varying color and line thicknesses throughout the period of the forecast. Again, the color indicates whether or not we expect it to exceed a return period, so it might be flooding, and the thickness corresponds to the flow in the river segment. The next service we produced to make these results accessible to people is a data service. Like most global data sets, like GEOGloWS and the ERA5 data, you can get the results to this model in bulk in NetCDF formats. But we found that can be prohibitive to those that we work with, since they don't really want to download the entire planet's worth of streamflow data. They have their watersheds, the perhaps upstream of a reservoir, their area of interest, and they really just want information about those few river segments that most impact their decision-making process. So we developed a data service, and on the top right of the slide, I've got a list of some of the products that you can get from our data service. From the historical and forecast data, we derive a lot of derivative products, which are statistical summaries or computing return periods, different kinds of averages to make the data more useful so that the user can get precisely what they need and get on to making the decisions that impact lives and property wherever they are. And this data service is accessible for free over the internet. So there's some patterns which I've briefly illustrated on the bottom of the slide. We also produced a Python package that automates querying this data service, as we found a lot of people work in Python for their analysis. I'd like to show a quick video of how this works also. So this is demonstrating the web app also. The first, we zoom in, find a river segment we're interested in, and can view the graph. But to demonstrate using that same pattern I just had on the slides, we'll go to a new tab, type in the pattern, get the identifier number for that reach segment, and fill that into our URL bar. And what we get back is a CSV of stream flow for just the stream segment that you're interested in. And this is really useful because it enables a lot of web applications, more targeted analysis without needing to download huge data sets and process them for your specific need. And so through my remaining time, I'd like to spend it describing some examples of how we develop these services, or how these services that we developed were used to impact decision-making at local levels. I've got 3 examples. One is in Honduras, the other in Guatemala and Nepal. And some are related to floods directly, some are water quality. We found that these services really enable quite a bit of science. And so these are representative of the wide gamut, not just flooding that these services make or provide data for. So first deals with Hurricanes Eta and Iota, which crossed through Central America in November of last year. I've got some maps on the left showing the paths those hurricanes took. Eta came first. It damaged a lot of infrastructure, claimed many lives. And importantly, in the context of Iota coming in a couple weeks after, it destroyed some of their water monitoring infrastructure. Some of the gauges which monitored inflow to reservoirs were disabled, and this hindered their forecasting capabilities. And that hurricane also put the El Cajon Dam, which I've got pictured on the right, at near capacity. So they've now got a reservoir nearing capacity, and they have limited forecasting capabilities, which were dampened by the first hurricane. And the dam operators were left with a hard situation of how do I control the releases from my reservoir so that I can be prepared for the coming hurricane, but I also don't want to lose too much water that I've just collected in the storm. And they have all these competing needs. And so they need good information, which was in short supply. So they used the GEOGloWS service to guide them during that process. I've got some graphs here, which came from an analysis we did after the fact using information from some of the gauges which survived the first hurricane. The red line shows what those gauges observed, and the shaded regions show different statistical values from our ensemble forecast. And really, this analysis deserves a presentation all into itself, but to grossly oversimplify, we found the model performed quite well, and this proved to be a valuable source of information to the dam operator so that they could avert further potential disaster if the reservoir were to fill the capacity or suffer any damage. The next example I'd like to talk about comes from Lake Atitlan in Guatemala. This is a lake known for its beauty and clarity, brings in lots of money for tourism, and sustains a town nearby. When the lake started to suffer water quality problems several years ago, some researchers started to investigate the cause of the blooms, see what can be done to remediate them. And those researchers needed dependable streamflow data coming from a good hydrologic model since there was insufficient river gauging infrastructure around the lake. And so they used the GEOGloWS data because it was free and it was running in an operational environment, so it was dependable. And importantly, that the data service that I described enabled them to get just the information they need, use our Python library to build and integrate it into their analysis scripts and help them move on with their research. I see I'm approaching my 15 minutes, so I'll wrap up quickly here. The last example I have is from Nepal. Many countries in Nepal and in the rest of the Hindu Kush Himalaya region have problems with frequent flooding. But again, like many places around the world, struggle with having early warning systems and monitoring infrastructure. So I've got some images here, which came from a news article where we had built a series of apps and web services, which are derivative from the global services, which I described. And a local teacher was using these web apps and services and noticed that a flood was coming. The year before, they had experienced major flooding and destruction. And so that the following year, when the flood season started, they were able to use these services to avert further potential damage. And the locals were very grateful that this global service provided potentially life-saving and property-saving information. So suffice it to say, we believe that this global hydrologic service approach has really provided valuable information and helped a lot of people solve real problems. Leonardo and Walter have already attested that these are difficult things to work on. There are many challenges we're still working on, and we're working to validate, calibrate, improve the services, and so on. But thank you very much.